Hello everyone and welcome to this section. In this section, we're going to dig a little bit deeper into training, okay? And we're going to see how do artificial neural networks learn? How can we assess, for example, our training strategy or training technique? And what are the problems, what that we go through during training? And we'll also cover different training strategies, such as supervised, unsupervised, and so on, all right? The first step is, okay, how do artificial neural networks train? As we mentioned earlier, it's like, it's like in the same fashion as how humans learn, how babies, for example, learn to walk, okay? We try to show babies, for example, okay, that's how you walk, and then the problem is, because they don't know what happened, they keep falling, right? So it happens over this period of time. So we try to, for example, teach the kid how to walk, for example, how to, let's say, label cars, for instance, by showing all the training data sets several times, okay, until the actually baby capture it, until it actually learns, until their brain actually changes, for example, the connections between the neurons, until it's kind of, like well known. Or every baby, for example, by age, let's say, or kid by age of, let's say, 4 or 5, can classify, okay, can know how to walk, can know, for example, how to classify cars and so on. Why? Because in their brain, the network has been classified in a way, the neurons has been connected in a way to classify, okay, when we see this, that means a car. And that's what we're gonna do when we train our artificial neural network, by changing the values of the weight within, the connecting weights between the neurons, okay? So artificial neural networks, again, can be trained from experience or by example, using what we call training algorithms. They can establish relationships between inputs and the outputs, all right? During learning or our training phase, what happens in artificial neural networks can adaptively change our network weights, which is the connecting weights between the input to the hidden and then from hidden to the output, all right? Okay. We have different training algorithms that we can use for artificial neural network training, and they can change by accuracy, by speed. We can change the computational complexity and memory requirements as well, all right? Okay, so let's dig a little bit deeper into, okay, what are types of learnings that we have? So the first step is what we call supervised learning. The second one is what we call unsupervised learning. And then the last one is what we call reinforced learning, okay? So supervised learning, that's the exact same way as I showed you before, that we have, again, a bunch of inputs, bunch of outputs, and that's why we call it supervised. We keep posing all the input-output data to the network, okay? And then the network learns through experience, all right? The learning algorithms mainly evaluates the outputs, we'll call it make predictions. We compare the predictions to the true class or the true output. We calculate an error signal, and we go back and we actually update the network weights. That's why we call it supervised fashion. And that's actually what we're gonna use during our project. Several projects throughout the course is mainly supervised learning. The second type of learning is what we call it unsupervised learning. Here, we actually use unlabeled data. There is no label. We actually just show kind of, like input to the network, and the network on its own can try to classify. These are kind of, for example, like, different categories or different classes. So for example, we just show the data to the network, and in unsupervised fashion, the network can learn on its own, okay? And there's a very famous technique, so we call it k-means clustering. It can be used to actually classify, be used for unsupervised learning, okay? Here, because we don't have unlabeled data in this class, there's no way to assess the accuracy of our, of the structure suggested by the algorithm, which means that the algorithm might say, okay, all the red lines are class, blue lines are class, and green dots are classes. However, some other, technique can say, okay, no, maybe we can take some of these green ones and we can put them under the blue one, okay? And there's no point, there's no way of saying, okay, like which one is the true, we don't know. Because why? Because we don't have a label, okay? However, for supervised learning, we can easily actually measure the accuracy of our training strategy. The last one is what we call reinforced learning. And here, the learning algorithm kind of takes action to try to maximize what we call it the notion of cumulative reward. So whenever the network does something wrong, okay, we actually penalize it. Whenever the network does something right, we actually give them kind of, we give them some reward. So the network kind of strives to make or to improve that reward in a way, okay, or maximize the reward, okay? And it's actually reinforced learning is very like a hot topic, you know, like as of today, as of the recording of that course. And there's a lot of research is being done in the reinforced learning, because some of the techniques used in the reinforced learning have been able to, you know, beat the best, for example, chess player in the world, which is very like kind of disturbing in a way, that now we have kind of intelligence that's, you know, way better than any human per se. Okay. And over time, again, these reinforced learning techniques, the network learns to prefer the right kind of action and avoid the wrong one. Okay, why? Because it gets penalized when it does the wrong one, and gets, you know, kind of reward when it does the right thing. All right, that's kind of a quick overview of the different learning strategies. In this section, we're going to focus on the supervised learning one. All right. Okay, so let's take a look at how can we train artificial neural network in a supervised fashion or supervised form, because that's our main focus in this lecture. So as you guys can see here, this is kind of, you know, like artificial neural network that has a lot of inputs, have a lot of outputs with different layers. Okay, they have layer 1, 2, and 3, and so on. And let's see how can we actually train our network. So let's assume that we have our training data, which is xn and yn, where n indicates number of samples that we have. So we have, let's say, sample 1, 2, 3, and so on. What we do is that we show, okay, the network our training input x, and we show the network the desired output, with the true output y. Okay. Again, like kids and, you know, like humans, these networks in the beginning, we start to initialize the weights. So we put like random numbers because we didn't train the network yet. The problem is the network generates what we call the predicted output. We'll call it y hat, indicating predicted. And in the beginning, that predicted output, we'll call it garbage in a way. So it doesn't have any meaning because the network wasn't trained yet. In the first run, what we do is that we calculate an error signal, which is simply the subtraction or the difference between the prediction and the true. And that's why we calculate the error signal. And then we use what we call the cost function, which is the objective is to try to minimize the error as much as possible. Okay. And what we do is that we use the error signal to go back and change the values of the weights in a way. And we do that over several, what we call it, epochs. And that's a very important term, which is kind of how many times we go back and update the weights. And these are the kind of different errors, you know, as you guys can see in the beginning, there's a very large error. As we go over a number of epochs, epoch 1, 2, 3, and so on, you would see that the error starts to go down as we move forward. And that's how the network train, okay? We can obviously assess the network training as it goes forward. If we see, for example, that the error or the accuracy is getting better, that means, okay, we're heading to the right direction, or the network has been stuck, for example, in what we call it local minima problem. We're going to discuss that moving forward, okay? So that's pretty much what we do, for example, during training here, okay? Okay, and that's very important concept coming up, which is what we call the difference between training data set and what we call it testing data set, okay? In general, we take whatever data we have, we divide them initially to training set and testing data set. Training data set, which is, you know, let's say 75% of the data, we use to actually train our network as it goes over a series of epochs, as you guys saw here, until the error reaches a certain value, and then we stop, and then now we have a network that has been trained. Now we have a network with number of weights that has been adjusted in a way to minimize the error, okay? Okay, and that's the most important step. We take the trained network, we actually use a different data set. That's what we call it testing data set. To apply that testing data set to test the accuracy of the network, okay, or the prediction capability of our network. The key element or the key difference between training and testing is that during testing, the data has never been seen by the network before. So the network hasn't seen the testing data before. And that's the power of an artificial neural network, is that we can show it, for example, different images of a car, and then it learns, okay, when you see these features, that means a car. And then afterwards, we can download, for example, an image from the internet of a car that hasn't, you know, the network hasn't seen before during training, and it can classify it in a way, like perfectly, in a sense, during testing, all right? Okay, so that's what happened. We actually, after training, we replace the training data set, we'll call it testing data set, okay? And here I try to just kind of, you know, like an example. If you have, let's say, if we're trying to classify different sine waves, here we assume, for example, okay, the shape is the same, but let's say the frequency is different, for example. And then we can actually still generalize and can predict as well that this, for example, signal is a sine wave still, using the testing data, which is the data the network hasn't seen before, okay? So the next question we wanted to answer is, how can we assess our training technique? Okay. So the first step is speed of conversions. Okay. How many epochs did we need to actually perform the training? Okay. That's one important question. The second question is the generalization capability of our training technique, which means how can we allow the network to be able to generalize, which means even if the network hasn't seen these images before during training, using data, like testing data or testing images, the network can actually still classify the output correctly. And that's how can we do the kind of generalization capability of the network, okay? All right. And the next element or the next important step is what we call it, the training technique has to avoid what we call it premature conversions to local minima problem. If we assume, for example, that we have our, let's say, function, looks like this, for instance, what we are looking for is that we are looking to minimize the error, which means we're looking for what we call a global minima problem. We wanted to minimize the error on a global scale, okay, using all the map, all the data that we have, right? That's what we're looking for. The problem is the network, okay, during training can actually be stuck not in what we call the global minima, can be stuck in what we call it local minima problem. Yes, it's kind of a valley in a way, okay? We have an issue here, okay? It's kind of, it's still a minimum, but it's not global minimum, so called local minimum, okay? So that's one of the power of different training techniques, is to try to simply look for the global minima point, okay? And these are kind of, the values, the weights, they can be used to minimize the value of the function across the entire scale, okay? All right, okay. The next step that we wanted to discuss is how can we divide the data set, all right? Again, this kind of a guideline you guys can use. Again, we're gonna use different kind of strategies. Okay, so the first strategy is we take the data, we divide them into training and testing, okay? Let's say we divide them, for example, to 75% training and 25% testing, all right? We use, again, the training data set to train the network over various number of epochs. We update the weights. Once we have our trained network, we use our testing data, which is data that the network hasn't seen before, to perform classification, to test our network capability, okay? There's another strategy, which is, okay, if we divide the data into, let's say, 50% training, 25% testing, and 25% what we call it validation set, okay? So what do you mean by validation set? Validation set can be used simply to perform what we call it cross-validation, okay? Which is, in a way, during training, okay, we try to assess the accuracy of the network, okay, to avoid what we call it the local minima problem. Okay. Our main concern during training is what we call it the overfitting problem, which means that the network might be focused on the details of the training data set and it avoids generalization. It doesn't generalize anymore. Okay, and that's one of the main challenges that or problems that we wanted to overcome during training. Okay, so overfitting simply occurs when the algorithm starts to focus on the training set kind of details, okay, at the cost of generalization capability, which means you might find that actually during training, the accuracy is getting great, it's getting better, the network is getting perfect, maybe reach 96%, okay? However, when we apply testing data set, the network, accuracy might be 70% or something, which means the network starts to focus on the details of the training data set and it doesn't generalize anymore. And we try to avoid this at all costs, okay? We wanted the network to perform generalization. We don't want the network to just learn, for example, the details of, let's say, 100 images of cars, but when we show it, for example, different images from the internet, it doesn't classify them. We don't need this. We need the image to be general enough to actually be able to classify all images of any car we show it, okay? All right. And that's one of why we use what we call cross-validation data set, which is kind of a portion of the data set that can be used during training to see, are we heading to the right direction or are we overfitting the data? All right, okay. All right, and that's all what I have for this section. I hope you guys enjoyed it and see you in the next section.